All right. I was working on the plan for the rest of the semester, but didn't get a plan done yet. But at least what I know is we're not running 11 labs. I don't think it's possible to fit a course project into that schedule with 11 labs, right? Because we don't have any weeks any breaks for all the weeks. If you look at the schedule, right? So if we use the previous schedule, we're running the lab 11 right before the Thanksgiving break. And it seems like the calendar for mines after Thanksgiving is pretty much just the final exams, right? That's what you guys have, and a little bit different from what where I came from, but which is fine. I mean, we probably can only run like 9 labs, I think. So I'm gonna pick up the good ones or important ones. So give you the time to work on a PCB design. What's that?
I know that in past years, ITs have mentioned that they got 2 dropped labs.
Yeah, I heard about that.
Will we have that?
Yeah, I heard about that. Yeah, I can consider that. Yeah, I think we should, right? Just if you are not getting a good grade, I can let you drop. Is that called drop the lab? That's what you call.
1 lab?
No, I mean 1 or 2. I don't know. If you only have like 9 labs, probably let you drop 1. Right? So remember that the goal, because we have been working on the same technology, the same board for so long. I have learned the timers, and for the rest of the semester will be ADCs and signal acquisition for the rest of the semester. It's basically just ADCs, right? Either use a microphone, you record your voice and replay it, or just record it, whatever, digitize it. So that's basically for the rest of the semester. Since you don't have too many things on the microcontroller. PWM, ADCs, timers. What else? You sometimes you have DACs. Oh, digital ports. Yeah, that's something we won't be able to get to, but there will be lectures on it. I didn't see any code available on his website, so I will see if I can find some libraries to let you guys use it. Actually, I2Cs and UR and SPI are pretty important. What's that?
So you said that you will be getting rid of 2 labs and doing the final project instead?
That's what I'm considering, yeah. Is that reasonable?
Yeah, I was just curious. I
Yeah?
just wanted to clarify that I heard you.
Yeah. Okay. Do you prefer 2 labs or just 1 project? Since the goal is to let you build a microcontroller system on the board, so during the career fair, anytime, like in the spring or anytime, you can tell them you have done some system level design with the microcontroller instead of just playing with the development board, right? So it's different. Since my undergraduate education, I didn't build a embedded system like from scratch, but I know it's super critical, especially during the interviews. They want to know you have done that, starting from the power supply. So I don't want to let you guys miss that super critical part. When you are asked to design a system as an engineer, where to get started, right? So you have to consider the power first. So how do you get a power in? There are so many different ways. You can use a jack header, you can use USBs. So most recently, USBs are getting super popular. If you look at the schematic, actually all the components being used for this microcontroller is basically just the power system, the filters, and the pin headers, right? It's just a pin. And this USB to serial converter, that's probably the most complicated component you have on the board. That's it. You power this up, get this one connected to the USB, you will be able to program your own board. I think that's pretty awesome. And you can add a lot of peripherals. So since we are not completing the entire board, I mean, the entire board is not difficult as well, but we are not doing that, you can pick up whatever you have to do, but you have to propose it to me and have to prove it, right? Otherwise, we'll just do, I'm gonna just probably just give you 3 to 4 options to follow. It could be, since we have learned the peripherals on the board. So it's probably the best idea is to reuse it and just adding something new to it, instead of just directly grab something totally new that we have never learned in the class. Okay, but not everything. For example, if you just do the speaker part of it, then we just use the audio amplifier over here, right? So in addition to whatever you have over here, the USB to UART converter, and the microcontroller chip, and the speaker audio amplifier, right? That's all you need. If you are doing IRs, like remote control or something, you need this IR LED BJT switch, and you'll need a decoder, the receiver, the decoder, and you need all the rest, all the power, USB, right? Voltage regulator, like here, and the chip. It's important to have the programming feature on the board because you may have to debug it, right? So if you have to debug it, you don't want to unsolder it and put it onto some of the dev board you have and program over there, then put it back. So you have to solder and unsolder all of the pads on the board, which are little tiny pins. They are not attached to the board very in a solid way, so it's going to delaminate. You don't want to unsolder and solder these little tiny pins like these ones for many times. So the best way to do that is, so you can see this is still not a final product because you still have the programming, it's still under the development phase, right? You have to program it. So that's why you have to identify the pins being used for the snap programmer. I haven't looked into that yet, but it should be just several pins, right? Very simple, just several pins. And these pins are connected to the USB to UART and then to the microcontroller. That's how the program is being transferred from the snap to here. So these ones, this USB is the mini USB, the bigger one with a bigger header, because that's the UART communicating with PuTTY, right? So the snap, keep in mind, the snap is not doing UART. Snap is just downloading program to the microcontroller. So this mini USB, the bigger one, is the UART one, and also providing power to the circuit. Why I know that? You see, the USB comes in, D plus, D minus. These are just the two data lines, and ground, just 4 pins from the USB connector. Very simple. And V bus is a power supply, 5 volts. So from your computer or laptop, right? 5 volts comes in, and this is a little fuse. I haven't seen that before, but let's use it. It must be necessary, I think, for some protection. And USB power supply comes in, it's just a wire, right? So V bus after fuse arrives here, and that one getting fed into the voltage regulator. It's very simple. If you learn this in the future, you'll become very confident about building systems because you know how to develop all these power supply modules or how to put a power supply on the board. So V bus comes in. This voltage regulator is a commercial chip. It's input and output. You ground it, input and output. You can get your desired output, which is 3.3 volts. That's it. Very simple, right? So the 3.3 volts is here available for you to use to power up your microcontroller. So it seems like the microcontroller is the 3.3 volts logic, and this is the USB to serial to UART converter. Okay, so the USB signal D plus, D minus gets into is there another intermediate board somewhere else? USB DM, right? So it's here, USB DM, and USB DP here. So USB data comes in here, and output is TX and RX. So see RX and TX. So you got UART. It's a converter, okay? It's a USB to UART converter. Make sense? So we need this one to do what? To program the board. Okay? Pretty simple, right? It's power supply, a little USB to UART converter, the chip. That's it. Then add your other peripherals, sensors, buttons, whatever, as a project. So in that case, I'm gonna remove probably two labs to let you guys work on the PCB and the programming for your design as well. So always the first step should be have everything connect to your microcontroller board on the dev board instead of directly design the PCB, right? You have to verify that all the logic, the connection, hardware connection works. Okay, then convert it to a PCB. Okay, if you have an idea, you want to start working on that project, one or two people on the team, okay? And the first time, I don't know when yet, but probably will be right after the fall break, maybe. I'm gonna replace it with a PCB lab. So it's gonna be PCB and programming. Okay, because PCB tutorials I'm not letting you guys using whatever I'm teaching right now, but there will be a easier one, I think. Won't give you really nice marks on the board, but it's easy to follow and very quick. So I had high school students can follow these tutorials and get it done in one day and get a layout done just within one day. It's a very simple technology to learn, actually. Okay. Schematic, layout, and build the library parts by yourself. Self-defined library parts, components for the PCB. Any ideas? Feedback? Yeah, good?
So you verify the design on your PIC board, and then it's all programmed on there, and then you would
Yeah.
solder that on a different board and be a standalone thing.
Yeah, yeah. So you have something to add to it. You got a breadboard, right? So you have the sensors and whatever actuators, buttons to be plugged into that breadboard, and you have jumping wires connect to a PIC board. You program it. You're confident it's working, functioning. Then look at the connections, convert it to schematic. Okay. Then send it out for fabrication. That's the process for design. What's that?
What software are we
Oh, Eagle PCB. Yeah, it's over here. What's that?
Can we use Altium if we
Yeah.
don't use
Yeah, sure. So the Eagle PCB tutorials are here. If you would like to follow, okay, go to my website, tutorials and resources, Eagle PCB, for tutorials. So you can probably find out the Eagle interface is slightly different from the ones we have, the newer versions. You have to know that Eagle has been it's not discontinued, it's not being updated anymore because they put it in Fusion 360. It's the same interface, almost the same interface. So it's okay to learn Eagle. In the future, if you want to transfer to Fusion 360, it's still the same same interface. So you can pick that up really quickly. And for library device, in the Eagle, you will see will be footprint instead of package. It's the same thing. It's just the pins and pads defines all the dimension on the board. So that's called a footprint in the newer version, but it was called package in the older version. So you have a symbol and a package to form a device that I can directly grab from the library and place it in the schematic. So we can explain that later, but you can follow the first one, the second one, and I believe after the second one, you can get a really simple voltage divider PCB, right? Okay, so know how to do things first. Then you can move to the microcontroller's PCB. Okay? I mean, you can probably reach here in like 2-3 hours. 2 to 3 hours. You can reach here. And the next step will be self-defined library, because sometimes the Eagle library or the SparkFun library you download it to your Eagle folder, they may not have that component that you want to use. Let's say the one, let me see which one we may not have. For example, this one is not really common, not very common component, for example, okay? So the library exists in your Eagle software, doesn't have this component. So you have to build it by yourself or download it from anywhere. There's a company called Snap EDA, I think. You can download that component and put it in your Eagle folder. You can just search for that component and you can directly use it. Because it's not a PCB class, so we are not requiring to design the self-defined libraries by ourselves. So as long as you can get a PCB out, then we are fine. So have something to talk about during the career fair. And they won't ask you if you drew the library by yourself. Usually they wouldn't, but unless it's a PCB position, they'll ask you if you know how to build components by yourself. Okay, let's just do a very quick job. As long as it's functioning, it's working, we are fine, I think, right? For the IR stuff, IR real quick. So the IR signal is a PWM waveform, and the frequency for that waveform is 38 kilohertz. Okay, so which is 38 kilohertz? Which one? Like this one or this one?
Top one.
Yeah, the top one. So the PWM, the faster ones, right? And you can see this is 50% duty cycle, but the real PWM is not 50%. You have to know that. And that duty cycle is not super sensitive to the duty value here. So for example, if you have a 10% duty cycle for these pulses, or you are using like a 15% or 20%, I tested. It's not affecting anything. But 50%, 60%, I don't know. Don't do that. It's too much. So usually 10% is a good value to use. So the question is why the IR signal are pulses instead of just directly digital signals. So it's being modulated or being decoded by the decoder. So if you are sending pulses, it converts it to a 1. What's that?
That way it doesn't get confused with any like ambient or background.
Yeah, that's one of the reasons. Correct.
IR.
Yeah, because ambient light has IR signals as well from the sun, from anywhere, right? So if it's pulses, the decoder you can design the decoder to only recognize or identify the pulses. Then after a certain number of pulses, you just define a voltage. Actually, this is wrong because whenever you see pulses, it's showing a voltage 0. Let me show you the real diagram. See? So I showed you this on Wednesday, I believe. Right? So pulses, and definitely if you zoom in, it's not 50%. Right? So way lower than that. So pulses will give you a logic 0 out of the decoder. And there's a time delay. There's a time delay over here. So let's think about one design problem here. After you have this signal available at the output of the decoder, okay, how do you read it? How do you read it into the microcontroller? What are the techniques you can use to read it based on your experience in the past few weeks? What you think? You got digital signal out, right, at a certain frequency. If I'm showing you this signal here, show one example. It's just one line. It's not parallel. It's just one line. It's a serial signal. So.
Could we do like what we did with the UART where you're taking the first, second, third, fourth, like from least significant to most significant bit?
Mm-hmm. So you need a certain protocol, right? Mm-hmm. Yeah. So whenever you transmit the signal to a microcontroller with a certain frequency like this one, do you remember what's this number? So this is a character 0. So in the ASCII table, 0 is 0x30. It's a 1 byte. Okay. However, what you see as the output is basically just this: low for a certain period of time, and high and low. Right? You have to know the bit rate. It's called the bit rate, or the frequency of this signal, so you'll know that this long line here is actually 4 zeros. It's not like 1 0. So when this signal is being fed into the pin of the microcontroller, what should you do? Let's think about it, brainstorm on that. How to deal with it? You know data comes in, and you want to read it, and put it into the register. I mean, that's the easy part. It's just to make an array, like a list or array, in your C program, right? So you want to start reading it. You can either code it up in software, right? After a certain period of time, use a timer to read it. Use I mean, there must be a function to read, right? So is that called the pin read or something? Definitely, if you set up that GPIO pin on a microcontroller to be a input pin, and you click MCC, it's going to generate a several functions to let you read from the pin. So you can read and set a timer and then read, right? Just keep it reading. If you know the frequency, you can read in the middle of the data. So read 4 times during this period. Or if we don't want to write up the protocol by ourselves, we can also use UART. So there are UART modules in the microcontroller. So UART has both RX and TX. Let me draw this.
So we should do like a jumper pin to the RX pin?
Yeah. So this is my controller. This is RC0. Why RC0? Because that's the pin connect to the decoder. You have a decoder. I believe you got output, so the other two has to be VCC and GND, right? Have to power it up and ground it. So the IR signal comes in. These are like this, right? PWM signals. The decoder is able to transform that into a digital signal like this with a certain frequency. How do we know which frequency we are generating over here by the decoder? I mean, can we program the decoder? It's a trap. It's a trap question. Let's think about it. So make sure you understand what's going on. How do we define the frequency over here? How do we define the frequency?
Isn't it just based on the signal that's coming in?
Yeah, it's based on the signal comes in, right? You are not programming this guy. This guy is really simple. It's just a digital circuit, convert PWM into this, that's it. Not programmable. So this data comes in, okay? Depending on how you read it. Otherwise, just basically low and highs. Depending on how you read it. So you have to define a certain rate. In here, for UART, I think we are using UART 2 for this one. I was looking at the map. Because schematic shows you that the output of decoder is connected to RC0. So it will be great if RC0 is what? So UART, if you want a UART to take the data in, so UART has 2 ports, right? RX and TX. What is RX? Receiving. TX, transmission, right? Transmitting. So it will be great that RC0 is exactly RX. Okay? So data comes in, we directly do whatever in UART, the function. It's called UART, I remember it's ART, whatever, okay? And that's read, right? Dot data ready or something? Whatever, so this is reading into it, right? Oh, so when data is ready, you do a UART2.read. So this function will take the data in, okay? And return it to a variable, okay? Whatever. Just put it, whatever variable in there, okay? So it will be great, this is RX, but I was looking at the website. look at the pin out here. Is RC0 showing an RX somewhere? See RC0 slash, so it's multiplex, right? However, is any of these showing an RX? No. Okay, so if you wanted this to be taken into the microcontroller within a certain frequency, you have to use UART1 or UART2, but usually we use UART2. Why? Because if you look at the schematic, which one is being occupied for serial communication, for sending data to monitor? See here, RX1, TX1. So what is being used for that? UART1. So UART1 is occupied. All right. So we have to keep that USB mini plugged in. Why?
For power to the
Yeah, yeah, it's power. Yeah, also for data, right? But whenever we don't use the UART1, I'm saying I just want to use UART1 for something else. It couldn't, because you still have to plug this in to power it up. It's connecting UART to it. So if you, because UART1 is being occupied, if you still want to use UART1, there might be some potential issues. I don't know what they are, but it's good to use UART2 because it's not being occupied, right? Do you have UART3? Do you have RX3 somewhere? I'm not seeing that. Okay, so we only have 2 UART modules. So UART1 is occupied, so we are using UART2 to take in that IR signal. Okay? If this is being read by the UART2 port, and we want to display it in your laptop, what should we do?
Take the TX pin from UART2.
And do what? Oh, here? And do what?
Send it to the laptop.
How? These on the PCB, right? But you only have one USB port, right? Sometimes, I don't know if you can multiplex the two different USB ports at the same time. Let me see if I've done that. No, I haven't done that. So data is already taken by the microcontroller. You can do whatever you want,
Oh, okay.
right? So how to display it over here? How to display it over here? Hmm?
Print F.
What is printf?
Well, they have the when we enable our UART,
Yeah.
we say serial.
You are what?
To STDI.
But you are what? Yeah, you are what? It's already within the microcontroller in the memories. You can do whatever you want. You can give it to the TX of UART1. So UART1 has what? RX and TX as well, right? So it's just a variable. You give it here, right? So what's the function to write it? What's the function to write it to TX? Like you are right? What's the function? Remember, you have done that for like millions of times. You just have ignored that. What is it? What's the function to print? Print, right? So print is a UART TX function. So whenever you print, it's sending that whatever in the program to TX through UART1 to the laptop. Make sense?
Is that default UART1?
Yes, UART1.
Okay.
Yeah.
Just making sure.
Yeah. So the transmission rate here, we just use a regular one. Okay? And the transmission here, you have to define it. Okay? How that is getting defined? You have to define only here or both. You have to know what you are doing here, right? So you are having, like, for example, this long. This part, you want to define that one as 1 bit. Right? So you have to do that for your PWM, which is CCP1. That's the one we're using. You have to know what kind of what. So you have to know what you are writing in here. wait. So the PWM is writing this PWM function to the LED, right?
So you need to know what frequency that's going, or?
Not that one. You need to know this. You need to know the. You know what I mean? For example, this is the 1 bit. This is 1 bit, right? So within that bit, you can have a lot of PWM functions, right? If you take one of them out, it's basically this, right? Okay. So definitely you need to design your program to not having this one wider than this, right? That's the bottom line. And you don't want to, like, for example, this is a 1 bit, and you are having just two pulses. Usually it's not the case. We have like multiple ones. I don't know how many, like 30, 40, I don't know. It's not that important though. But you do need a lot of pulses in there. So I want to let you guys know it's not very sensitive to the number of pulses. And it's not sensitive to the width here as well. Since I tried different duty cycles, it's not changing the result. So if it's not sensitive to the number of pulses, which means it's not sensitive to the period as well, right? Okay? Just let you guys know. So in that case, you just make sure that you have like 30, 40, whatever in here. We already gave you the numbers, just follow. It's gonna work. If you change it, you're curious about it, you can change it. I think it's one of the tasks in the inLab. It's asking you to change the period of this one, but not the duty cycle, but the period, to see if you are still getting correct data. So that's the way to verify what's the possible period you can use to not making mistakes for the output. That's not important though. We don't have to worry about that unless we are working on that specific task in the inLab. So for now, my question for you guys is, what is defining this length or width for this period? To define that this is just 1 bit instead of multiple bits. How do you define it?
Is it software?
It's software, yes. I mean, what is actually this doing? What is this actually doing? You turn on the PWM. The PWM is going to run, right? It's outputting that thing for a certain period of time. So what is this one actually doing here? You turn it off, right? After a certain period of time, you don't want to run the PWM anymore. You just stop it. That's how you define this bit rate. Now let's look at the inLab code, how that works. It makes a lot of sense here. Let me show you that piece of code here. This code does that job. Take a look at it and let me know. I'm going to give you 1 minute to read it and see if that makes sense. I'm going to ask you a quick question after that. Oh, so actually, which one is the PWM module we are using for this code? Which module? PWM2. So what's the pin output for PWM2?
CCP2.
CCP1 actually. Let's take a look at it.
Is it like RB5 for 1 and then C1 for 2 and C2 for 3?
I couldn't remember. I couldn't even remember that much. Let's take a look at CCP.
Yeah.
We can get back to that later, but no, let's take a look at the code for now. What's happening? Can you group them? Can you just group a certain lines of code and so you know they are doing one job? It's actually pretty simple. What's going on? What is this one doing?
Loading a duty value.
Do the duty value, and it's gonna start it, right? So after this line, you are going to see the PWM waveform as the output. Then right after that, you want to do what?
Define your bit period, how long you want it to be on.
Yeah?
Delete it.
You turn it off after that, right? You set a timer right after that line. That's it. You turn on the PWM, set a timer, and wait here if the flag is not on. And when the flag's on, get out from the while loop, turn it off. That's how you define what? Let's get back to the paper.
How long one bit is?
How long one bit is. Or, aka what?
Baud rate.
Baud rate for what?
UART.
Yes. Make sense? Do we have to use 9600?
Not necessarily.
Yeah? What are the options?
You could do anything, right? Anything that the UART can read.
Here.
No.
That's a question in the inLab. Let's run one of them and see if that makes sense. Am I losing anybody? Losing like 80% of you guys? No? You're good? Doing good? It's recorded. Come back to revisit. Okay? Sorry, it's super abstract. If you don't have a board to play with, right? You have to imagine, have to create a computer system in your mind. So let's see. Okay, so what's the parameter? What are the registers to define the baud rate? That's 2 bytes actually. Baud rate high, baud rate don't have L, but it's L. Okay, and I have to use the equation to calculate it. Let's see if I have it here. It's right here. So we we are going to choose 0, 1, 1 for this register. So that will give us this entry, and eventually we are using this equation to calculate the baud rate. Just like let you guys know, we don't have choices. It's already chosen. Okay, you can change it, but it's not necessary. Okay, we don't have to do it. So keep that in mind. If you see this equation in the data sheet, you have to change this one to 4. That's the equation to calculate baud rate. All right, so this register, the lower byte is concatenated to the higher byte to form a 16-bit number, and that's a number being taken by the microcontroller, and eventually it's gonna output a certain baud rate for you. We don't have to worry about that. It's all designed by the digital engineer in microchip. So what we need to do is just to give a correct number to this register. That's it. Okay, how do we get the right number though?
Solve for it.
No, this calculation algebra. Oh yeah, that's right, software as well, yes. But I mean, to get the number here to be used, right? Definitely software, you have to put a hex number in your program to assign to these registers, right? However, before you know these numbers, you have to plug in the numbers in this equation to calculate it. So this is the equation you want to use. It's FOIC. What is FOIC?
Frequency oscillation.
64, right? Yeah, 64, but the 64 one. So it's going to be 64 megahertz divided by 4. And these are all constants. And desired baud rate. That's bits per second. So if you look at this one here, for every single entry, for example, for this one, what we want to do here, that's 9600 is the number on the left-hand side of the equation, right? Plug that in. So 9600 equals what? 64 mega divided by 4. And that's x plus 1, right? X plus 1. Just calculate x. Easy. Let's see if we can get the right answer here. So it's going to be 16 mega divided by 9600. Okay, and minus 1. So that is 1665.67. All right, that's x, right? That's x. But x has 2 bytes. So let's use programmer one. And that's a decimal number. It's 1 665. I think we have to round it to like 1666. Okay?
Yeah.
So it's gonna be 1666. So what's the hex number? 682. So it's basically 0682, right? For 9600 bits per second. Alright, so I already did this for you. What is here? What is this? Oh, you forgot?
06.
Alright, what is this?
822.
Okay. What about this? Bit period. You know the bit rate, just 1 over this guy, right? But convert to microseconds, 1 over 9600. What is this? Midterm problem. It's asking for the counts, number of counts you want to put in timer 1.
It's just the same. You can explain it.
Yeah, so what you know? What is the frequency counting timer 1? Timer 1's LSB. 16, right?
Yeah.
With a 1-to-1 per scalar. Alright? How many counts? So remember we were here, right? We need to define the timer 1 to make this happen, remember? So we need a certain number of counts to make that happen. If this period, so how long is this? I'm just asking you. How long? How long is it?
104 micro.
16.
Right? 1 over 1600, right? And 9600, right? So this is time, right? That's the time. So if you're given with the time to find the counts, this is what you want to do, right? This is what you'll do. Because time, this is also time, it's per second. So second got cancelled.
Isn't the bit rate per second though?
Yes.
So you would want to divide by 16 mega to get seconds to cancel.
No, I mean, but 1 over 9600 will be, yeah, same thing probably. 1 over 9600 will be time. Will be second per bit,
Oh right.
right? So 1 over 9600 times the frequency will give you the counts needed for timer 1 to count, to reach what? To reach this width here. Make sense? Questions? Good?
If you get like an odd number or like a decimal, do you just round up?
What did you get? Odd number? Oh, you mean a fractional? Or the decimal digits?
166 6.66666.
I believe it's. This is the inLab code, okay? I believe it's this guy. Okay, so in the inLab code, it gives you several options to pick up the baud rate for which UART. You are what? You are 2, right? So it's just a list. You just pick up this one, it's a constant. Then in here, the code I just showed you, that's the one you selected, right? That's the one you selected. Is timer 1 counting for that number of counts
No.
by this line?
Yes.
Yes, why?
You take the full length of the timer and subtract that
Yeah.
length, so you're only counting that
Yeah.
much.
Right? So this total counts minus whatever the desired count is, setting up a starting count for the timer. So the remaining counts will be exactly the number of counts you need to give you a 1 over 9600 second width for that bit, for one bit. Okay, any questions on this? Revisit this, okay, later. I know it's kind of abstract.
Could you show your calculation on how you got like 13 through 33? Because I've also got.
Oh, really?
66.
Just do 16 mega divided by 9600. It's 1666 point something. So if it's,
Oh.
I would have rounded up. I would have done 1667.
Try this one. Probably I was because UR2 is not using this baud rate. Sorry, but the equation is right. Okay, so it's just here.
That one gets you 1330.
Yeah.
Do you just ignore whatever the decimal is?
Yeah.
All right.
Because the number counts, right?
Mhm.
You can now have decimal for counts. Less than 5, so less than 0.5. Other things, minor things I have to talk about. Keep in mind, I probably have to replace this figure. It's not right because pulses are giving you 0, right? So for the emitter, for the decoder, you can see the decoder diagram on my website. What's the most sensitive wavelengths for the decoder? It's over here, right? Over here. It's giving you the best output. So what about the LED though? The LED also has a certain wavelength. That's a peak wavelength. Okay? And for the IR emitter, and it's, if you tilt it or if you detect it from a 10 degrees off from the middle, and you'll see it's getting attenuated drastically. So this is a diagram to get the attenuation here. So here's the 10 degrees. I can see the gain, right? 0.4. How much is getting attenuated? That's for the LED, for the emitter. Okay. And other things you need to know.
The reason that diagram wasn't right is because the LED's active low or active high?
No, it's LED is. Oh, you mean which one?
The very one at the top that you said was wrong that you wanted to replace.
Yeah. So it's active low. Yes. So pulses will give you a 0. Let's see. Oh, time delay. So the time delay is something you cannot get rid of. So the issue for that is, if you have a certain time delay always, you won't be able to change the baud rate too much. So the baud rate cannot be less than this, right? Has to be well above that width over here. That makes sense, right? Anything else? That's it. See you on Wednesday.